All right, we're moving. All right, so this week we're going to be doing worksheet 9, wave nature of light. I went ahead and gave you the equations for this guy just because it's important to keep them organized, and I wanted you guys to be able to see how I kind of think of them, like defining each equation. So I guess I'm just going to jump right into it. We're going to be doing this wave nature of light just to kind of get us on track, and then next week I'm thinking I'm going to do two worksheets where I'm going to do like optics, lenses, and mirrors, and then just pushing up with what we're doing this week. But some of this stuff I think that you guys are going to see, you're going to learn on Thursday if you haven't already. Okay, so just like looking at our equations here, we have these two kind of big types of questions that come out of these wave nature things, and that can be like the double or single slit experiments and the thin film interference. So let's just start by talking about the double/single slit scenarios. So obviously you can have like the bright or dark condition, and then based on kind of the context of the question, you'll know if you're dealing with double or single. As you'll see, it's like they're the inverse for each other. So the double bright is the same as the single dark, and the double dark is the same as the single bright. So they flip-flop with each other. And that has to do with a pi shift or a phase change, basically. And essentially what's happening is, it's there's like a sine wave, right? So it's just a wavy wave. And whenever we do that 1/2 switch, there's going to be a lambda over 2 shift. But then if you do that lambda over 2 shift twice, it's basically like 1/2 plus 1/2, so that equals 1. So then you go back to the other. So with each subsequent one, it kind of goes back and forth. You're going to really see that with the thin film interference, as we're going to discuss shortly. Other than that is just to kind of remember that, although we draw the thin film, I'm just going to do a quick double right here. We draw it like this, and we'll have like a triangle coming out, like something like this, right? We have to remember that if we're defining this as our central max, let's say central max bright, that there's a sine wave here, or there's waves here where it's going to go like peak to trough to the O is the highest on that middle trough. So it's going to be, wow, this is like the best wave I've ever drawn for this kind of question. It's like perfectly symmetrical right here. Anyway, yeah, so you're always remember that this 0 position is always going to be the highest compared to this -1 and this 1 position. Other than that, you'll sometimes be asked to find the width right here. So let's call that x. So that x value right there only represents from 0 to 1. So if you want to find the full width of that central max, it's actually going to be 2x. I guess we'll kind of see that there, and I'm kind of jumping the gun, but just to keep that in mind, kind of what's really happening within these diagrams is, yeah, there's like a max peak attendant to that central bright. All right, so we kind of discussed the single and double slit. Let's go to the wavelength in non-air substances. So basically, this is going to really pop up with thin film. Obviously, light goes through a bunch of stuff: glass, oil, Gatorade, whatever. But there's going to be a different wavelength within those mediums. And really taking a step back, there's going to be a different speed of light through those mediums, where the speed of light through air is basically the same as that in a vacuum. So that's kind of predefined. So we can really use that as our standard there, where we have that lambda air divided by the index of refraction of the substance. So I'm going to call that N substance. And that actually equals the lambda of the substance. So let's say we have light traveling through blue Gatorade. We're going to have the lambda of it in air. So let's say completely random, it's 50 nanometers, divided by the index of refraction of that substance. And that's going to actually equal the wavelength through blue Gatorade. Because let's say we have a red light that's shining through air, and then it hits my blue Gatorade that I'm holding. First, it's going to be, we have that wavelength through air, but then we also need to consider the wavelength through the Gatorade there. Cool. And then the thin film, yeah, I mean, I think it's going to be best seen in an example here. We have to consider the constructive versus destructive interferences. Yeah, they switch, like their parameters switch with every phase whenever there's a phase shift. But we'll get into that. Like I don't even want to like kind of explain that theory until you see the question. All right, so just looking at number one, this is going to be a pretty quick worksheet. Light of a wavelength of 680 nanometers falls on two slit experiment to produce an interference pattern in which the third order, where remember m equals third order, so for those experiments looking back, we'll always see it's like m lambda or m plus 1/2 lambda. So third order, bright fringe, right? I'm just going to pause there. Excuse me for taking forever, but so we already know so much. We know we're dealing with a double slit experiment. We know that it's double bright, and we know that we're dealing with the third order, right? So the m equals 3. Okay, so in which the third order bright fringe is 38 millimeters from the central fringe, which is on a screen located 2.8 meters away. What is the separation between the two slits? So what are we looking for? We're looking for that variable d, right? So that d is going to be the measure of like center to, like in the case of a double slit experiment, it's going to be like that, so center to center. Or in the case of a single slit experiment, that's d, right? So just remember that for both. Anyway, so let's just dive into this question number one. I'm going to draw out our diagram so I feel like it's easier to visualize in that way. So we have light coming through. It's going to go like this. We know that we're dealing with third order, right? So I'm going to put a 0, 1, 2, 3. We're looking for this d value. I've got my notes here. We're given what x is. We already know what that is. Call that theta, and this is L. We know that already too. You're often going to be finding this angle when, well, obviously, I mean, it's in the equation, but one way or another, you're going to need to find that angle through some tangent, where tangent, remember, is opposite over adjacent. Okay, so we remember from the question, we're told double slit experiment, double bright, and we're looking at the third order, so we're looking at 3 there. So then, which equation are we going to use? You guessed it, d sine theta m lambda. D sine theta equals m lambda. So d sine theta equals m lambda. We're just going to want to rearrange because we're solving for that d. What we don't know, though, is theta. So we're going to find theta through tangent function here, where, opposite, so x over L. Theta is just going to equal the inverse of x over L, which is, 38 times, that's right. (38 times 10 to the 3 divided by 2.8. This whole thing. Oh, excuse me, I forgot to write our inverse function here. All right, and then theta comes out to be equal to 0.778 degrees. So now we know we can plug in for here. M is given, remember it equals 3. We're given the wavelength here, it's 680 times 10 to the minus 9, nanometers, divided by sine, that angle we just got. And that all comes out to equal 1.5 times 10 to the minus 4 meters. Yeah, so really small distance between them. That's kind of it. So we're going to do the same kind of question here, but this time we're going to be considering. I guess you kind of should have waited for you guys to see that. All right. You guys can pause if you're watching at home. Now we should do the same thing except with a double slit experiment here. So erase all this. All right. Next, this double slit experiment. So here we have, we want to know how wide is the central diffraction peak on a screen that is 2.3 meters behind a, that wide slit illuminated by a 558 nanometer light. Okay, so we're dealing with central diffraction peak. So what's our m going to be equal to? 1. Because we want to know how wide it is on both sides. Actually, you guys wouldn't really know that yet unless you have like a really good intuition of this. So let me go back and explain that later. But what we do know is we're dealing with a single slit And just by definition of these single slits, like the fringe pattern will alternate light and dark, right? So there's going to be that wave here. I guess it'll be easier to see if I go like this. And I think someone's shining a light in here. And we want to know what the width is, how wide this central diffraction peak is. So that means we're going to be looking at this, right? Because remember, it's going to go like, wait, that's not right. That should be down there. See, I told you, I did the best I could on the first one. I peaked. Gotta be like this. All right. So remember here with a single slit, it'll be alternating, right? So here we'll see bright. So that's going to be bright, but here we're going to see dark. And that's just because, just by definition of the fringe pattern, where the fringe pattern formed by a single slit consists of alternating bright and dark fringes, right? So then obviously it's going to be dark also, right? So that's dark. We're asked to find this width of the central diffraction peak, right? So this is kind of what I talked about earlier. So this is that unit x right here, and we can find that unit x with this angle theta. However, we want to find the full width of it, so we're actually going to be looking for 2x, right? 2x at the end. So we want to get the full width. Other than that, what we're given here is, we're given d. We're given dl too, right? Yeah. And so we're going to need to use that tan function again in some capacity. So what do we do here? We consider our equation. We're dealing with a single slit, and we're observing the dark. So single slit dark, what's our equation for that? D sine theta equals m lambda. Give me one sec, I'll move this. Yeah, okay. The first thing we need to do is, we already know everything except for that angle theta. So we're going to first find theta. So theta will equal that sine inverse lambda of d. Okay. You're going to plug in everything. Theta is going to come out to be equal to 0.919 degrees. And then in part 2, knowing theta, we're going to be able to find x because we also know L. So how do we arrange this? Tan theta equals x over L. We already know L, so L tan theta equals x, right? So x, just plug in everything, will come out to be 0.037 meters. And then we're done, right? No, we're not done, because we need to find the full width, which is times 2. So don't mess this up. So just multiply this whole thing by 2, and then really that full width you're going to get equals 0.0738 meters. And let's box that. That's our final answer. Cool. That's single slit experiment. We're almost done with the worksheet here. Good progress. All right, let's keep it going. Let me just get you guys see that. And this next one, we're going to be kind of exploring the difference between the orders and how they affect the equation, and then based on what order we're looking at, what would be the expected parameters? That being, how would you expect the angle theta to behave? How would you expect x, the distance between them, to behave? So this is kind of to build an intuition on solving these questions. Let's just get into that. I really hope I'm not muted right now. Okay, thanks. I've done that before. I've done a full 45-minute session and then realized I've been muted the whole time. Yeah, that's a feels great moment. Okay, number 3. Here we have light with a wavelength of 632.8 nanometers, and that's creating a second order bright fringe at 52 degrees, and then it passes through a grating, right? So what is the wavelength of light that creates a first order bright fringe at 20.6 degrees? So expectantly, like the 53.2 is bigger than the 20.6. But let's realize what equations we're going to be using here. So in both cases, we are going through a grading. So, it's not a single slit. So that's telling us it's double slit. And then again, they're both bright fringes, so double bright. So what's our equation? That's going to be d sine theta equals m lambda, right? And we have two scenarios here. Effectively, we have two scenarios. That first one being, right? We have d sine theta 1 equals m. One of them is was it first order and second order? Yeah, first order, so m1, and then lambda 1. Oh no, I think it's the same. No, it's the same, right? No, we're looking for the wavelength. Yeah, okay. So lambda 1, and then d sine theta 2 equals the other order, the second order one, and then the wavelength we don't know, lambda 2. And all right. So what we have to do here is recognize what's consistent between them. And that's the grading, right? They go through it's the same grading. So effectively, they have the same D. I should stop saying effectively because it's the truth. They do have the same D. All right. So if we just do some rearranging and we get everything equal to D here, we'll see that we have M1 lambda 1 over sine theta 1 equals M2 lambda 2 over sine theta 2, right? So the next important thing to recognize here is what is known and what is unknown. So we know what M1 is, we're given that as first order. We know the wavelength, that's 632.8 nanometers. And we know what theta 1 is, that's 53.2. Next, looking over here, we have the first order. I guess that's confusing because I said 2. Because this first one is second order. Yeah, so I'm just going to write it out so we don't get confused. So what I wrote is M1 is actually in respect to the second order one. So don't get that confused. And that wavelength there was 632.8 times 10 to the minus 9 divided by sine 53.2. So yeah, just be careful of that wording right there because although it's the first scenario, we're actually dealing with the second order bright fringe with that wavelength. Okay, and for the second one, it's the first order one. We don't know what the wavelength is, but we do know the angle. Oh, right. Yeah, I would use it. 20.6. So what we have to do now is just solve for that lambda 2. So you multiply by sine 20.6 on both sides. Lambda 2 comes out to be 556 nanometers. There. Done. So yeah, not that tricky of a question there. Next, let's look at number 4. All right, number 4. Covered in chalk. After these sessions, I have like chalk in my mustache. It's like going in my mouth. It's on my computer. All right, so we have light of a wavelength 541 nanometers sent through 2 slits, a double slit, projected on a screen 4 meters away. The slit centers are that unit D. What are the locations of the first 2 double slit maxima to the right of the central maximum? It's a lot of information here. But the first thing let's establish is this is a double slit bright scenario. So what equation are we going to use? Is that d sine theta equals m lambda, right? Oh. So d sine theta equals m lambda. So we can just draw out our diagram here. We have the light coming in. So this is D, right? We already have D. I think they gave us L. Yeah, they gave us L. this is L right here. The light's going like this. We're looking for the 2 to the right of the central maximum. So I'm going to call that 1 and 2, right? So we have the first order and second order ones here. So the first thing let's check out here is, and we're also solving for like, what's this distance? So let's call that x1. What's this distance? Let's call that x2. Right. So the first thing we need to do is find their respective angles right here, right? Yeah. So let's start with the first scenario. So with the first scenario, we're just gonna solve for theta 1. So just move inverse sine and divide by d. We're gonna see that equals, right? So first order, the wavelength is 541 times 10. Oops. Erase. Times 10 to the minus 9 divided by 13.2 times 10 to the minus 6. And again, I forgot my sine function, so that's going to be inverse sine right there. And theta 1 comes out to be 2.35, right? So all we need to do next is use our tangent equation, because we know L, we know what this theta is now, but we don't know what that x1 is. So we can say tangent theta 1 equals x1 over L. So x1 equals L tan theta 1, which equals 0.164 meters. All right, so that's for x1. X1. Done. So then for x2, you would expect both the angle to that theta 2 to be bigger and that x2 to be bigger. And if you guessed that, you're going to be right, because when we solve, you're going to see exactly that. So let's solve here for x2 now. So same setup, completely the same setup, except this time, we're looking for that theta 2. So I'm just going to go straight into the inverse sine. I want to get rid of that there, make it clear. So go straight into that inverse sine minus 1, inverse, and then now we're dealing with the second order parameter. It's the same wavelength as before, divided by that d, which is, oh wait, my decimal's wrong. No, wait, that's right. Minus 6, bam, theta 2, bigger, 4.7. Next thing, we're going to have to use that tan function. I'm going to skip to the x2 equals 4. That's that L tan 4.7. Ooh, hope you guys didn't hear that sound. That's the sound of my chalk holder metal scratching against the chalkboard. x2 then equals 0.329 meters. Bam. Number 4, done. All right. So next we're going to be discussing thin film interference. That's question number 5. Before I really get into it, I just kind of want to explain just a little bit of the theory behind it, just very quickly though, just so I'm sure you guys are going to get the full explanation in lecture. So let me just jump into this real quick. So effectively, every single time like light goes through one of these thin film interference questions, so it's like something like this, right? You're gonna have like either some materials like this, or you're gonna have the scenario where it's like air, oil, water, and then in both cases, like you'll have like light coming in, and obviously through each thing, it's gonna be like reflected, right? So it's gonna be like bam. And same thing here, like you're gonna have light coming in, normal incidence right here, it's gonna bounce off there, potentially go here, and then probably just bounce all the way off like that, and it won't continue. That's like probably the setup. But I mean, I guess like it could also just like continue through. It like depends on the question, right? So effectively, with these questions, when light reflects off a surface of a higher index of refraction, it's gonna have a lambda over 2 phase shift, right? And what's index of refraction? That's that unit n, right? So I think I looked it up, and So like for air, n equals 1. Yeah, so for air, n equals 1, n equals 1.5 for oil, and n equals 1.33 for water, right? But it only reflects, like the phase shift will only occur when it reflects off the surface of a higher index of refraction. So looking at this scenario right here, we'll see, yeah, there's going to be a phase shift right here. But then on this scenario, you know, it's going from a higher to a lower, not from a lower to a higher, so no phase shift. And a phase shift is generally just like it's that, like adding the 1/2 to the lambda, right? So with one phase shift, that's why you'll see our equation become m plus 1/2. But if there's two phase shifts, it's going to be m plus 1/2 plus 1/2. So just effectively equals, like it cancels out, like it'll cancel out, right? And you'll just use the order that they're telling you. That's kind of a confusing way to say that. I don't know why I said it like that. So like in this scenario, you have one phase shift. So we know there's 1 lambda over 2 phase shift. I'm just going to write times 1, right? So how do we express that? It's going to be, you know, that 2d equals, or even looking at our equation sheet, it's going to be 2d equals m plus 1/2. I'm going to say lambda of the substance, right? Because we know what it is, like the wavelength through air would be given, but you need to remember to calculate them for each one of these subsequent ones per that equation also in the formula sheet, where lambda over air over the index of refraction of the substance, right? So that's how you'll be able to find that, where this equals, where lambda substance equals lambda air divided by n substance. Okay, so that'll probably give you those n values, unless it's like explicitly what you're solving for. And then this is constructive interference right here. And then in the case where there's 2 phase shifts, like I said, you're gonna have 2 lambda over 2's, so times 2, that is equals 1. Like, you know, 1/2 times 2 equals 1. So the lambda will just be, you know, be equal to 2d equals, so 2 phase shifts, which right times 2 equals 2d m sub. And effectively what this is, it's like every single time like the light goes through a substance where it travels slower, that there's going to be a phase shift. So you can imagine in air, it's like basically like the fastest it'll ever be as if it's in a vacuum. So yeah, other than that, any integer lambda informs constructive. And when the path length, you know, like a change in x, let's say, so delta x difference is 1/2 lambda, then it's going to tell you that it's destructive interference. So like here, I would say this is destructive just because oh, shoot. No, wait, 1 second. Forget that. Yeah, forget that. And then when there's a phase shift, they switch. So that's how I know in this scenario, this one's constructive, because there is a phase shift. But if there was another phase shift, then it would go back to this integer value, and then there will be destructive. Yeah, I think. So yeah, if there's a phase shift, they switch, and there's two phase shifts or 2 pi shifts, the flip cancels out, and they return to the normal. Yeah, okay, yeah. So yeah, that's constructive. Like this is an example of constructive. All right, so let's do our thin film interference question. So here we have a wedge with a length L. It's formed between 2 glass plates of an index of refraction of 1.45. They're separated with a height h. So the greatest separation is that h value. And then the interior of the wedge is filled with a material with n equals 1.15. Light is normal incident to the wedge from above. At what x value is the first bright band for red light wavelength 600 nanometers. All right, that's a lot of text there, but I'm just going to draw this diagram and walk us through what we're dealing with here. So we're dealing with a constructive because we have one phase shift, right? So I like to draw my index of refraction on each portion. So that's that, right? And we know that this distance right here is h. We know that this right here is L. We're looking for the first order one. So we're just looking for x1. And we know that there's going to be that distance d at that point. So between the plates, it's going to be that distance d and x1. And then we can imagine it's like an angle here, right? So how's this light behaving here? So it's coming in, bouncing right there. It's coming in, bouncing right there. From here, we're going from higher to lower, so we're going to have that phase shift right there. It's going to go like this and then bounce up here like that. Right? Okay. So we have, all right, this times 1 pi shift, or phase shift. We're dealing with the first one, so let's just solve this guy out. So which equation are we going to use? The constructive where m equals 0, right? The first one. So we're going to say 2d equals m plus 1/2 lambda of the substance. Remember, because now, like within that liquid or whatever they said, the unknown is there. We don't know how the wavelength is behaving, but we do know the wavelength in air. So we just have to solve all this stuff out for d. So I'm going to start solving for d up here. So then d equals, I'm just going to plug in everything. So m equals 0 plus 1/2. And then what's that wavelength in air? It was 690 times 10 to the minus 9 divided by 2. And then what was the index of refraction? Remember, that's 1.15. And the reason why I have like this portion right here is because of, y sub equals y air divided by its index of refraction. You solve that, and d comes out to be 1.304 times 10 to the minus 7 meters, right? With this, we now have enough to find that x1 value. So, just per the ratio of h over L will always equal like d1, well, let's say d1 over x1, right? So if you're looking at the next one, like d2 over x2, that ratio stays true. And what we're looking for is this x1. So we just have to do some rearranging here, and we'll say that x1 equals d1 L over h, d1 L over h, and then we can just plug in everything. I apologize, it's going to be a little cramped here. That's going to go 1.304 times 10 to the minus 9, 8.5 times 10 to the minus 2. That's like that centimeter distance. And then divided by the 0.035 millimeters, so 10 to the minus 3. And then x1 comes out to equal 3.17 times 10 to the minus 4. Sorry, I bet you I'm off screen right here. Yeah. And there we go. That's thin film. So that was a pretty brief one. I'm sure that on your guys' final exam review, you're going to have a lot longer of one. So we'll make sure to go through that one on my exam review sheet. Other than that, Friday session, 8 a.m. Come with your homework questions. Even if like I think that maybe I had the impression that students thought that they needed to have like completed the homework by the time they came. Like, no, even if you tried it, even if you just like looked at it and you're a little bit confused and needed help, like I'm happy to do it. Also, if you guys ever want me to do a video explanation for one, just send it to me. I can pretty quickly have that back to you, especially since like Thursday night. I'll just crank that guy out Friday morning and it's done. So yeah, thanks for watching, guys. Send me your homework questions. I love to solve them and post the video. I feel like an influencer. So thanks, guys. I'm going to end the recording here. Email me with your questions.